Few scientists have experienced a discovery that changed the course of human history while receiving so little recognition for it. Fewer still have watched from a distance as the world celebrated others for work they helped make possible. Lise Meitner was one of those rare figures. She helped unlock the secrets of the atomic nucleus, contributed to one of the most important scientific breakthroughs of the 20th century, escaped Nazi persecution, and played a crucial role in explaining nuclear fission. Yet for decades, her name remained overshadowed by others. Her story is one of brilliance, perseverance, and moral courage in an age defined by both extraordinary scientific progress and unimaginable human tragedy. Lise Meitner was born in Vienna, Austria, in 1878. She entered a world where opportunities for women in science were extremely limited. Universities across Europe were largely designed for men, and many scientific careers were effectively closed to women regardless of talent. From an early age, however, Meitner showed an intense curiosity about mathematics and physics. She was fascinated by understanding how nature worked beneath the surface. While many children accepted the world as it appeared, she wanted to know why things behaved the way they did. This desire for deeper understanding would define her entire life. Education was not easy to obtain. In Austria, girls were generally excluded from the academic pathways that led to university. Meitner had to overcome barriers that male students never faced. She pursued private study, worked through demanding examinations, and refused to abandon her ambitions despite the obstacles placed before her. Her determination paid off. In 1901, she entered the University of Vienna, becoming part of a generation of women slowly pushing into higher education. There she encountered one of the most influential physicists of the era, Ludwig Boltzmann. Boltzmann was a legendary scientist whose work helped establish statistical mechanics and deepen humanity's understanding of thermodynamics. More importantly for Meitner, he was an inspiring teacher. Unlike many academics of the time, Boltzmann welcomed talented students regardless of gender. His lectures conveyed not only scientific knowledge, but also the excitement of discovery itself. Meitner later described him as one of the greatest influences on her intellectual development. Under his guidance, physics became more than a subject. It became a calling. In 1906, Meitner earned a doctorate in physics, becoming one of the first women in Austria to achieve such a distinction. This alone would have been remarkable for the period, but she was only beginning. She soon realized that the center of modern physics was shifting toward Germany, particularly Berlin. The city was becoming one of the world's great scientific capitals, attracting researchers who were exploring radioactivity, atomic structure, and the emerging mysteries of the subatomic world. Determined to participate in this revolution, Meitner moved to Berlin in 1907. The challenges immediately returned. Women were still treated as outsiders in many scientific institutions. At first, Meitner was not even allowed to enter certain laboratories through the main entrances. In some cases, she had to work in basement rooms because women were prohibited from using facilities intended for male researchers. Yet she persisted. In Berlin, she met chemist Otto Hahn. The partnership between Hahn and Meitner would become one of the most productive collaborations in 20th century science. Hahn was a skilled chemist. Meitner was a gifted physicist. Together, they combined expertise from two disciplines that were increasingly becoming intertwined. Radioactivity had become one of the most exciting areas of research. Scientists had discovered that atoms were not indivisible as once believed. Instead, they contained internal structures capable of releasing enormous amounts of energy. New particles were being identified, strange transformations observed, and long-held assumptions challenged. For researchers like Meitner, it felt as though an entirely new universe was opening. Working together, Hahn and Meitner spent years investigating radioactive substances. Their research required extraordinary patience. Experiments often took months. Measurements had to be repeated repeatedly. Tiny traces of material had to be isolated and analyzed with extreme care. Scientific breakthroughs rarely arrive as dramatic moments. More often, they emerge from years of meticulous work. Meitner excelled in this environment. She possessed a combination of theoretical insight and experimental understanding that made her unusually effective. Colleagues respected her intelligence, precision, and ability to tackle difficult problems without losing focus. Over time, her reputation grew. She became one of the leading experts in radioactivity and nuclear physics. This was an extraordinary achievement for anyone, but especially for a woman working in an era when many institutions still viewed female scientists as exceptions rather than equals. The scientific world itself was changing rapidly. In 1911, Ernest Rutherford proposed the nuclear model of the atom, suggesting that atoms contained a dense central nucleus. This transformed the direction of physics. Researchers increasingly focused on understanding the nucleus and the forces governing it. Meitner was at the center of this effort. As new discoveries accumulated, scientists began realizing that the nucleus held tremendous secrets. Hidden within it were forces and energies far greater than anyone had previously imagined. The question was no longer whether the atom could be understood. The question was what humanity would do once it understood it. By the 1920s and early 1930s, Meitner had become one of Europe's most respected nuclear physicists. She held a senior research position, published influential papers, and contributed to a field advancing at breathtaking speed. Yet outside the laboratory, dark forces were gathering. Political extremism was rising across Europe. Economic instability fueled radical movements. And in Germany, a political figure named Adolf Hitler was moving steadily toward power. For scientists like Lise Meitner, the coming years would bring challenges far greater than any scientific problem. The future of physics was about to become inseparable from the future of the world itself. As the 1930s progressed, the world around Lise Meitner began changing in ways that no scientific achievement could shield her from. Inside laboratories, nuclear physics was advancing at an extraordinary pace. New particles were being discovered, atomic structures were being mapped, and researchers across Europe were competing to unlock the deepest secrets of matter. But outside those laboratories, political events were rapidly transforming Germany into one of the most dangerous places in the world for many of its own scientists. When Adolf Hitler became Chancellor of Germany in 1933, the effects on academic life were immediate. Jewish professors were dismissed from universities. Researchers lost positions they had spent decades building. Scientific institutions that had once attracted talent from around the world became increasingly shaped by Nazi ideology. Brilliant physicists, chemists, and mathematicians began leaving Germany, seeking safety elsewhere. Lise Meitner found herself in an increasingly precarious position. Although she had converted from Judaism to Christianity years earlier, Nazi racial laws classified people according to ancestry rather than personal belief. To the Nazi regime, Meitner's Jewish background made her a target regardless of her accomplishments or contributions to German science. At first, she managed to remain in Berlin. Her Austrian citizenship offered a degree of protection, and her international reputation made some officials reluctant to act against her immediately. She continued working at the Kaiser Wilhelm Institute alongside Otto Hahn, focusing on the mysteries of the atomic nucleus. Yet the situation grew more dangerous every year. Colleagues disappeared from institutions. Academic freedoms vanished. Political loyalty became increasingly important. The scientific community that Meitner had spent decades helping build was slowly being dismantled by ideology. Despite these pressures, the research itself remained fascinating. Physicists had become intensely interested in the possibility of transforming atomic nuclei. One of the most important discoveries of the era had come from James Chadwick's identification of the neutron in 1932. Unlike electrically charged particles, neutrons could penetrate atomic nuclei without being repelled. This opened entirely new experimental possibilities. Scientists began bombarding elements with neutrons, hoping to create new substances and uncover deeper nuclear processes. Among the most interesting targets was uranium, the heaviest naturally occurring element known at the time. No one fully understood what would happen when uranium absorbed neutrons. The nucleus was a mysterious place, governed by forces that scientists were only beginning to understand. Meitner, Hahn, and their colleagues became deeply involved in investigating these reactions. The experiments were difficult and often confusing. Results did not always match expectations. Strange substances appeared among the products of nuclear bombardment. Measurements suggested transformations that seemed almost impossible according to existing theories. Yet the team continued. Years of experience had taught Meitner that scientific progress often emerges from anomalies. The unexpected result is frequently more important than the expected one. Meanwhile, events outside the laboratory reached a breaking point. In 1938, Nazi Germany annexed Austria in an event known as the Anschluss. Overnight, Meitner lost the protection that Austrian citizenship had provided. She was now fully vulnerable to Nazi racial laws. The danger became immediate. Friends and colleagues warned her that remaining in Germany could lead to arrest. Opportunities to leave were rapidly disappearing as borders tightened and restrictions increased. For a woman who had spent over 30 years building a scientific career in Berlin, the prospect of fleeing was heartbreaking. Yet staying was no longer an option. With the assistance of colleagues and friends, Meitner planned a secret escape. The journey was risky. She had little money, limited travel documents, and no certainty about what would happen if she were stopped. At the age of 59, she was being forced to abandon her home, her laboratory, her possessions, and much of the professional life she had spent decades creating. In July 1938, she crossed the German border and escaped. The departure was emotional and devastating. She left behind not only her research environment, but also many personal relationships. The laboratory where she had worked with Otto Hahn for decades was suddenly inaccessible. A partnership that had helped shape nuclear physics was abruptly divided by politics and persecution. Meitner eventually found refuge in Sweden. The transition was difficult. She arrived without the institutional support she had enjoyed in Berlin. Research facilities were less developed. Resources were limited. She felt isolated and displaced. Many refugee scientists experienced similar struggles. Escaping danger did not automatically mean rebuilding a career. Yet even from exile, Meitner remained intellectually engaged. She continued corresponding with Otto Hahn, who was still conducting experiments in Berlin. Despite the political circumstances, scientific communication between them continued. Then, near the end of 1938, Hahn sent Meitner puzzling new results. His experiments on uranium were producing substances that made little sense under existing assumptions. Chemically, the products appeared to resemble barium, an element far lighter than uranium. This seemed impossible. According to prevailing theories, uranium might absorb particles or undergo small transformations. But no one expected a massive nucleus to split into much smaller pieces. The result challenged everything scientists thought they knew about atomic structure. During a walk in the Swedish countryside with her nephew, physicist Otto Frisch, Meitner began analyzing the problem. Together, they considered whether the uranium nucleus might actually be breaking apart. The idea was astonishing. If true, it would mean that a single atomic nucleus could divide into two smaller nuclei, releasing enormous amounts of energy in the process. Using Einstein's famous equation, E equals mc squared, Meitner calculated that the tiny loss of mass during such a split could account for the tremendous energy observed. Suddenly, the confusing experimental results made sense. The uranium nucleus was not merely changing. It was splitting. The process would soon receive a name: nuclear fission. It was one of the most important scientific discoveries in human history. And as 1938 came to an end, Lise Meitner was helping explain a phenomenon that would reshape science, warfare, politics, and the future of civilization itself. The discovery of nuclear fission at the end of 1938 marked one of the most dramatic turning points in the history of science. For decades, physicists have been investigating the atom, gradually uncovering its internal structure and hidden energies. But no one had fully anticipated what Lise Meitner and her nephew Otto Frisch realized during their analysis of Otto Hahn's experimental results. The atom contained far more power than anyone had imagined. When Meitner and Frisch worked through the calculations, they understood that the splitting of a uranium nucleus was not a minor event. It released an enormous amount of energy compared to ordinary chemical reactions. The difference was staggering. A small amount of matter could produce an extraordinary amount of energy. Einstein's equation, E equals mc squared, had predicted this possibility decades earlier. But now, for the first time, scientists were seeing a real physical process that demonstrated its implications. Frisch soon performed experiments confirming the phenomenon and coined the term nuclear fission, borrowing the word from biology, where it described the splitting of living cells. The scientific world reacted with astonishment. Within months, researchers across Europe and North America were repeating the experiments. Laboratories confirmed the results. Papers were published rapidly. Physicists immediately recognized that nuclear fission was not merely another discovery. It was a doorway into an entirely new era. The implications extended far beyond pure science. If one uranium nucleus could split and release energy, then perhaps the neutrons produced during that process could trigger the splitting of additional nuclei. This possibility suggested something revolutionary, a chain reaction. In theory, one nuclear event could trigger another, and another, and another. The energy release could multiply rapidly. Scientists quickly realized what this meant. Nuclear power might become possible. So might nuclear weapons. At the same moment that researchers were celebrating one of the greatest scientific breakthroughs of the century, many were also beginning to fear its consequences. For Meitner, these developments unfolded under deeply unusual circumstances. She had played a crucial role in explaining fission and interpreting Hahn's experimental results, yet she remained physically separated from the laboratory where the discovery had occurred. Living in Sweden after her escape from Nazi Germany, she watched as the scientific community absorbed the significance of a breakthrough she had helped make possible. The outbreak of the Second World War in 1939 intensified everything. Scientific research became increasingly connected to military concerns. Governments understood that nuclear physics might possess strategic importance unlike anything previously seen. Funding expanded. Secrecy increased. International collaboration became more difficult. Physicists suddenly found themselves working in a world where scientific knowledge could determine the outcome of global conflict. Many refugee scientists who had fled Nazi persecution settled in Britain or the United States. There they joined research efforts aimed at understanding nuclear reactions and assessing whether an atomic bomb could actually be built. Meitner followed these developments closely. She understood the science better than most people alive. She also understood the dangers. As evidence accumulated that chain reactions were possible, the prospect of a nuclear weapon became increasingly realistic. What had begun as an investigation into the structure of matter was evolving into something with potentially catastrophic consequences. In the United States, the Manhattan Project was eventually established. This massive secret program brought together some of the world's leading physicists, engineers, chemists, and mathematicians. Their goal was straightforward and terrifying: build an atomic bomb before Nazi Germany could do the same. Because of her expertise, Meitner received invitations and inquiries regarding nuclear weapons research. She refused. This decision would become one of the defining features of her legacy. Meitner believed deeply in science and discovery, but she was uncomfortable with the idea of contributing directly to the development of weapons of mass destruction. Having witnessed the rise of Nazism, experienced persecution, and been forced into exile, she understood better than many the dangers that political power could pose when combined with advanced technology. Her position was not based on scientific ignorance. It was based on moral judgment. She continued pursuing scientific research, but she chose not to participate in bomb development. Meanwhile, Otto Hahn remained in Germany throughout the war. Although he had not developed the theoretical explanation for fission himself, His experimental work was central to the discovery. As the years passed, the distinction between experimental discovery and theoretical interpretation became increasingly important in discussions about credit. Then came 1945. The war in Europe ended. Nazi Germany collapsed. But in August of that year, the world witnessed the full power of nuclear fission for the first time. Atomic bombs were dropped on Hiroshima and Nagasaki. Entire sections of both cities were destroyed. Hundreds of thousands of lives were affected by the blasts, radiation, injuries, and long-term consequences. For many physicists, the bombings created a profound sense of shock and reflection. Scientific achievement had become inseparable from human tragedy. Meitner was deeply disturbed by the destruction. Although she had not worked on the Manhattan Project, newspapers sometimes referred to her as the mother of the atomic bomb because of her connection to nuclear fission. She strongly rejected this characterization. She had helped explain the science, but she had not participated in weapon development and did not wish her work to be associated primarily with nuclear warfare. At the same time, another controversy emerged. In 1944, while the war was still ongoing, the Nobel Prize in Chemistry was awarded to Otto Hahn for the discovery of nuclear fission. Meitner's name was absent. Many scientists and historians would later view this as one of the most controversial decisions in Nobel history. Hahn unquestionably deserved recognition for his experimental achievements. But Meitner's role in interpreting the results and explaining the process was also fundamental. Without her theoretical insight, the meaning of the experiments might have remained unclear for much longer. The omission hurt. For years, Meitner had overcome barriers based on gender, nationality, and political persecution. Now, one of the greatest discoveries of the century was being recognized without fully acknowledging her contribution. Yet, despite the disappointment, she continued her work. Her reputation within the scientific community remained strong. Researchers around the world understood the importance of her contributions, even when formal awards failed to reflect them fully. And as the post-war world entered the atomic age, Lise Meitner found herself occupying a unique place in history. She had helped unlock the energy hidden within matter itself. But she would spend the rest of her life reflecting not only on what science could achieve, but also on what responsibilities came with such knowledge. In the years following the Second World War, Lise Meitner became something more than a physicist. She became a symbol of scientific integrity, intellectual perseverance, and moral responsibility. The world had entered the atomic age, and the discovery she had helped explain was now shaping global politics, military strategy, energy production, and humanity's understanding of its own technological power. Yet Meitner herself remained remarkably humble. She never sought fame and rarely spoke about her achievements in grand terms. What mattered to her was the pursuit of knowledge and the responsibility that came with it. Having witnessed both the beauty of scientific discovery and the devastation that scientific knowledge could enable, she approached the post-war era with a sense of reflection that many others shared. The atomic bomb had changed everything. Scientists were no longer seen merely as researchers working in laboratories. They had become figures capable of influencing the fate of nations. Nuclear weapons introduced a level of destructive power unprecedented in human history. For the first time, humanity possessed the ability to destroy entire cities in moments. Meitner understood this reality perhaps more deeply than most. She had spent decades studying the nucleus not because she wanted power, but because she wanted understanding. The fact that this understanding had contributed indirectly to such destruction troubled her. While she remained proud of the scientific achievement itself, she repeatedly emphasized that scientific progress must be accompanied by ethical judgment. Knowledge alone was not enough. Human wisdom had to keep pace with human capability. Throughout the 1950s and 1960s, Meitner continued speaking about science, education, and the responsibilities of researchers. She encouraged young scientists to pursue discovery while remaining aware of the broader consequences of their work. Her experiences under Nazism had shown her how easily science could become entangled with politics and ideology. This perspective gave her voice unusual authority. She was not speaking as an observer. She had lived through the rise of Hitler, the collapse of European democracy, forced exile, World War, and the birth of nuclear weapons. Few scientists had experienced so much of the 20th century's turbulence so directly. Recognition gradually increased as the years passed. Universities awarded her honorary degrees. Scientific organizations celebrated her contributions. Awards and distinctions accumulated. While the Nobel Prize controversy never disappeared, many within the scientific community worked to ensure that her role in the discovery of nuclear fission would not be forgotten. Historians also began re-examining the story. As documents, correspondence, and research records became more widely studied, it became increasingly clear how essential Meitner's contribution had been. Otto Hahn's experiments were critical, but so was Meitner's interpretation. The discovery of nuclear fission was not the work of a single individual. It emerged from years of collaboration, discussion, experimentation, and theoretical insight. Modern scholarship has largely restored her place in that story. Today, she is widely recognized as one of the key figures behind one of the most important scientific breakthroughs ever achieved. But perhaps her greatest legacy extends beyond fission itself. Lise Meitner's life demonstrated what determination can accomplish in the face of extraordinary barriers. She entered science when women were often excluded from serious academic careers. She established herself in one of the most competitive scientific fields in the world. She survived political persecution, escaped Nazi Germany, rebuilt her life in exile, and continued contributing to science despite immense personal hardship. At every stage, she refused to surrender her intellectual curiosity. She also showed that scientific excellence and moral conviction are not opposites. Many people assume that science is purely technical, concerned only with facts and equations. Meitner's life suggests something more complicated. Scientific discoveries affect real human lives. The pursuit of knowledge inevitably raises questions about responsibility, ethics, and the future. She never stopped thinking about those questions. In 1968, Lise Meitner died in Cambridge, England, at the age of 89. She had lived through a period that transformed humanity's understanding of the universe. When she was born, atoms were still considered indivisible. By the time of her death, humans had split the atom, harnessed nuclear energy, explored space, and entered the early stages of the computer age. Few people contributed more directly to that transformation. On her gravestone appears a simple but powerful description: a physicist who never lost her humanity. Those words capture something essential about her character. She possessed extraordinary intelligence, yet remained deeply aware of the human consequences of scientific progress. She pursued truth relentlessly, but never allowed ambition to eclipse conscience. She helped reveal one of nature's most profound secrets while reminding future generations that knowledge carries responsibility. Today, her name appears on schools, research institutions, awards, and even an element on the periodic table. Element 109, Meitnerium, was named in her honor, ensuring that her contribution is permanently woven into the language of science itself. It is a fitting tribute, for Lise Meitner did not merely help explain nuclear fission. She helped reshape humanity's understanding of matter, energy, and the hidden forces that govern the universe. And in doing so, she left behind a legacy that extends far beyond physics, a legacy of courage, integrity, and the belief that scientific greatness means little unless it is guided by human values.